Okay, now that we have gone over tension theory, which is the theory behind the limit states of yielding, rupture, and block shear, and the concepts of net area and then effective area, taking into account shear lag, we are going to implement what we've learned, and with that knowledge, use the design equations found in the steel manual. So you better have your steel manual next to you. If not, pause and go grab it, because it is vital to the next several hours or days, years of your life. All right. So if we're talking about the design of tension members, we're talking about chapter, if you go to chapter D in the spec, so this is about 2/3 back of the book, chapter D. This is where you start to want to have tabs, right? Chapter D starts on page 16.1-28. It is the design of tension members, design of members for tension. And there are a couple. We're going to focus on D1, the slenderness, which is a serviceability limit state, which we didn't talk too much about. But slenderness limitations, tensile strength, D2, and an effective net area. We're not going to go beyond that too much for chapter D. If you go to chapter B, which starts on page 16.1-11, but we're actually going to go to B 4.3, which is page 16.1-20. It's going to tell you how to calculate your net area. Right, about halfway down the page, it should say net area. It's going to give you some guidance on that. Okay. So chapter B is all about design requirements, and if you look at the beginning of it on 16.1-11, tells you, like, B2 talks about loads and load combinations, and it says go look at ASCE 7. Turn the page 16.1-12. It'll talk about the load and resistance factor design, which is what we use, and ASD, and those design basic equations with the phi factors or the omega factors. Bunch of things about design for different types of connections, fatigue, fire, interesting things to read, and then talking about eventually B4 member properties. That's where what we're in. We'll come back to these tables on page 16.1-17, 18, and 19. We'll use those in our design of columns and beams. But that's what chapter B is, okay? So we're in chapter D. We are also going to eventually talk about block shear. And so if you go to section J4, sometimes it's nice to have some tabs. Actually, there's a part in J3 that we're going to look at in a minute. But J4 has block shear starting on page 16.1-137. And then the block shear is on the next page. Another thing that we will likely, I'll talk about it in a minute, but chapter J is all about design of connections. That's what chapter J is. And it'll have information on bolts and bolt holes, which is something that we will need in calculating our net effective area. So this is all the spec, the specification. These are the actual design equations that decades and centuries of engineers have come up with to guide our design of steel structures. The beginning, the manual part, is where you will find some tables that utilize these equations and already have some numbers calculated for you. So tension members is part 5, which starts on page 5-1. Should be a little tab that says TEN dot. And you'll see there's design tables, and it talks about the assumptions of the design tables. If you switch to page 5-2, it talks about how they calculate the net effective area. Effective net area is assumed to be 0.75 times the gross. Oh, there it is. Use of table 6-2 for design members, page 5-3. So this is an assumption, right? This is where we start having assumptions in our tables. And so you have to always realize what assumptions these tables are making and if you're allowed to make those same assumptions. So, and then if you flip to page 5-5, you start to get into available strength of axial tension. Should probably, this is, yeah, because you can see up at the top it says it assumes an FY and an FU, right? So again, there's another assumption. But yeah, so it gives you axial tensile strength of a bunch of different sections again, the biggest assumptions, I'll write these down. Do I have them at some point later? I don't think I do. The design charts assume AE equals 0.75 AG and assume an FY and FU. They assume material properties. So whenever using these charts and tables, remember what your assumptions are, is the bottom line. I forgot to adjust this thing. Okay, so that is where we are navigating in the manual for tension member design. So, if we go to chapter D, right? What our first limit state for a member in for tension design is yielding. We had two limit states, yielding and rupture. Our first one is yielding. So if you go to the beginning of chapter D, which is page 16.1-28, we're looking down at section D2. Tensile strength. The design tensile strength, VTPN, shall be the lower value obtained of the limit states of tensile yielding on the gross section and tensile rupture on the net section. So our first limit state is yielding. Equation D2-1. PN, our nominal tensile strength, PN, is Fy, the yield stress, times the gross cross-sectional area. And Fy is our yield stress, AG, and for the limit state of tensile yielding, my phi factor is 0.9. So if I were to calculate the tensile strength according to tensile yielding, VTPN would be equal to VT Fy AG, make that a better F, Fy AG, where Vt is equal to 0.9. Okay? My second limit state, it says, is rupture on the net effective area. So now we're in, we look at the next one, right? D2B, equation D2-2. My yield, or my tensile strength for tensile rupture is the ultimate stress, Fu times AE. And my phi factor associated with the limit state of tensile rupture is 0.75. So you'll notice that the phi factor for tensile rupture is 0.75, but the phi factor for yielding is 0.9. Any thoughts about why that might be? If you think about it, rupture is the thing actually breaking. And it's something you really don't want to have happen, right? Yielding could lead to excessive deformation, but it may still actually have strength. Whereas rupture breaks and strength goes to 0. So you want to put a lower phi factor to reduce your tensile strength for the rupture limit state. So if you're calculating your tensile strength, right, if we do the same tensile strength, for rupture, phi t, pn, right? That little baby t is for tension. Pn, that's my my nominal tensile strength. FUAE, and again, phi t is now 0.75. So now we're going to talk about this AE, right? AE, my effective net area, is equal to your net area, AN, times a shear lag factor, U. So AN, it should say that in, right, if you go to section D3 on the next page, 16.1 -29, this is actually equation D3-1. where AN is your net effective, or your net area, and U is your shear lag factor. And it says that the gross area AG and net area AN of tension members shall be determined in accordance with the provisions of B4-3. Point 3, sorry. And that the shear lag factor is determined by table D3.1. Your net area, well, we'll talk about that. Yeah. So it says B4.3. This is page 16.1-20. I think I already said that, but. The gross 3A says the gross area of a member is the total cross-sectional area. The net area is the sum of the products of the thickness and the net width of each element. The biggest part we're going to talk about is computing the net area for tension and shear. The width of the bolt hole shall be taken as 1/16 greater than the nominal dimension of the hole. And then it also talks about for a chain of holes that are zigzagged, that are staggered, we're going to add the quantity S squared over 4G. So, this is for a diagonal pattern. It says for a chain of holes extending any part, the net width of the part shall be obtained by deducting the gross width from the sum of the diameters or slat dimensions and adding S squared over 4G. Where S is your longitudinal center to center. So longitudinal means, right, if you see it down here, S, same, right, actually let's just write it this way. Parallel to PU, transverse would be perpendicular, right? So this is my adjustment for a diagonal. It also says use 1/16 greater than the nominal dimension on table GA 3.3. This accounts for potential damage in fabrication, because when they're punching the hole, maybe they're going to make the hole 3/4 of an inch, but that 1/16 right around where they punch it might be damaged a little bit. We can't really count on that 1/16 of an inch for any sort of strength. So we're going to subtract that out. So if you go to table J 3.3, this is what it feels like you're just going back and forth in the manual. That's why it's kind of nice to have tabs and also maybe understand, right? Because chapter J is all about connections, so there's information about bolts. So table J 3.3, page 16.1 dash 130. It gives you, I'll give you a sec to get there. Hold on. Okay, page 16.1-130, table J 3.3. You notice there's 3.3 and 3.3 M. M would be metric. We're in America and we use inches, so we're going to stick with the not M one. But we have on the left the bolt diameter. So if you have a 1/2 inch bolt, they're going to punch a hole that is 9/16 diameter, which is actually just a 1/16 bigger for a standard bolt hole. In fact, if you look at 1/2 inch, 5/8 inch, 3/4 inch, and 7/8 inch, they're all just 1/16 bigger than the bolt diameter itself. 1 inch or larger, it's 1/8 of an inch bigger than the bolt diameter. And then to this, we are going to add a 1/16 of an inch to account for damage. So I got a 3/4 inch bolt. I'm gonna punch a hole that's 3/16 of an inch, but I'm gonna add another 1/16 to that I'm gonna pretend that the bolt hole is a 1/16 inch greater, right? Let's draw. Right? So let's say I'm gonna look at this in elevation, right? I have a plate. This is the cross section of a plate. And I need to put a 3/4 inch diameter bolt, right? Ugh. Right? Quarter inch diameter bolt. I'm going to punch a hole for that bolt that is actually 13/16 in diameter. And then when I'm actually calculating my net area, I'm going to subtract another. I'm going to assume that there's damage. This is damage. Damage makes bolt hole diameter equal to 13/16 of an inch plus another 1/16 of an inch. That's what this is saying. So in reality, I would subtract from my width, I would subtract 13/16 plus another 16th, which would be 7/8. There's also a note here about workable gauges in gauge is how far apart they are. 1-40. Wait, hold on. 1-7A. Oh, there it is. 1-52. Where was that? Maybe I was on 1-50. Okay. That means how far apart you can actually have bolts trained on angles. So this would be more for the design, but it'll tell you how far apart you can put bolts, or like that G, if you're looking at it, how far from one side of the angle you need to put your bolt holes. We don't delve into that too much, so here's kind of a summary. When I'm calculating my effective net area, I take my gross area, AG, and I subtract my nominal bolt diameter plus that 1/16 of an inch times the thickness, right? Here's my bolt hole. This is my thickness of whatever it is, right? If it's a plate, it's a little bit more straightforward, but with all the fillets and stuff of a structural piece, a structural cross section, like a T or a W section or something. Right. So, yeah. So this accounts for my bolt hole. Bolt holes. then this is where we add back in if we have staggered diagonal holes. You get to add back in, according to chapter B, you get to add back in a little bit of length, right? This is the length, and then again times the thickness. Actually, let me make sure that I read that correctly. This, right? The bolt holes you subtract out because you're actually subtracting materials to make space for your bolts. Diagonal holes, this is just saying a diagonal is longer than a straight line, right? If we have something like that with bolt holes like that versus bolt holes like that, you get to add a little bit more length that way. So this is my net area, right? Gross minus your bolt holes plus a little extra if you have diagonal. Now, you have your effective net area. You multiply your net area, AN, by a shear lag factor. So let's go to chapter D, right? Equation D 3.1. We already talked about that. And it tells us how to calculate U. According to table D 3.1, which is just on the next page. Eccentricity. So a shear lag factor is basically reliant on the eccentricity of the connection, which how far away from the right, eccentricity is your distance, how far you are from the centroid, right? If you were, say you were applying a load right at the center of something, right? Then your eccentricity of that load is 0, but if you were applying a load off, this is not particularly talking about, this is just defining eccentricity, but, right, If it was off center, then this would be your eccentricity. Eccentricities often invoke additional moment, which is why they need to be accounted for. Your shear lag factor is based off of how far away your connection is from the centroid of the section, because loads act at the centroid of a structural steel cross section, and how long your connection is. If you remember, the longer a connection, the more time the force or stress has to disperse to the entire cross section. So if you have a really long cross section, right, if your length gets really, really big, if you look at this equation right here, if your length gets really, really long, then this starts to go to 0, and you have you have a shear lag factor of 1, and you don't really have to account for it. If you have a really, really short connection, that number increases and your shear lag factor will be less than 1. So shear lag factor is less than or equal to 1, right? Because you're modifying your effective net area. You're modifying your net area. You're reducing it due to that phenomenon of shear lag. So I'm going to do some calculation, discuss different cases of shear lag factors. Okay? This is where it all gets kind of funny. Not funny, but hopefully I don't lose you. So, case 2. We're looking at this case. Right? All tension members except HSS, so except hollow steel sections, where the tension load is transmitted by some but not all of the cross-sectional elements, by fasteners or by longitudinal welds in combination, or by longitudinal welds in combination with transverse welds. Alternately, you could use case 7 for our W section or case 8 for angles. Case 2, if you look at case 1, let's just go back to that one. All tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds. If every single cross-sectional element is connected, you can use a shear lag factor of 1. What I mean by that is if every flange and every web, both legs of an angle, the web and the flanges of a T, all 4 sides of an HSS, actually it says, no, you can't do that. But, yeah. So, we're looking at case 2. So I want to show you what case 2 looks like. If we have, you can look at the little pictures. That's what is always helpful. There's little examples. So we have, if only the web of an I-beam is connected, maybe, right? If only the flanges of an I-beam are connected. If only one leg of an angle is connected. I think this last one, this is a T. This is if only the flanges of a T are connected. So this were the case, let's see, I get to draw. Right, if we're looking at the first example, that means right, if that's my I-beam, looking at it isometrically, and I'm attached a connection plate, right? With some bolts, I don't know, 2 little bolts, and my load right? Because I'm only connecting the web when my force starts to spread out, right? Well, it might not even get out of the web. You know, if you think about pulling that little, you know, the middle of that of the web of my I-beam, you're pulling on that, and the rest of it, the 2 flanges, and maybe even parts of the web, might not be fully engaged. So you can't count on the entire cross-section when you're calculating your net area for rupture, right? If you're talking about way on the other side, let's see. That looks terrible, but yeah, probably be more like that. If you're talking about the other side, the whole thing might be in, for yielding, you can count on the entire gross cross-sectional area, but where you have this connection, you're not going to have the entire cross-section. So this is what it means by tension load transmitted by some, if not all, by some but not. Okay? In this instance, we've only got the web, and even then we're not sure if the entire web's getting involved. And then we would have to look at, the other thing you need to look at is look at the X bars. And look at what they're actually asking. They're actually X bar, right? Yeah. I'm just going to say this, and we'll look it up in a second. X bar in a table in the dimensions. So what do I mean by that? let's go to, let's see, let's look at a W shape. Any W shape would be fine. Go to page 1-26. I don't know. This is where I really should, hold on. So it's best, and I'm gonna pull up, I have a PDF of the 14th edition, so the page numbers will be slightly different, but if we look at a W shape, right, your dimensions are in that first, it's part 1, the very beginning of the manual. I'm looking at, this says like page 1-18. Doesn't really matter. It's got slightly different numbers. But what I want to look at is this little picture right here. Right? If I look at this shear lag factor picture, it says like if I connect my connection is only on the web, the eccentricity, right? You'd see that picture, you see where that X is. If I go to this table, no, it doesn't have. Actually, I was getting them mixed up. So, if we're looking at this one, right, my eccentricity would actually be, if I'm looking at a cross section, let's see. Let's draw. Where's my little there? There it is. All right. Could make it a symmetric I-beam. Okay. And I have that, and maybe I have bolts through it. I want to know my eccentricity. It would be, according to that picture, from like here to there. So this would be the thickness of the web divided by 2 plus that plate thickness. And it's an example of that eccentricity. For case 2. Right there. Now, if you're looking at a T, we'll talk about that. Yeah, we're looking at a T. It'll tell you. So keep in mind that these might not be readily available, is what I'm trying to say. like if we look at this case right here, either the flanges or a T with the flanges, it says use this. Here, I'll draw a T. And it says that my X bar is the distance from this centroid to here. So if I go to my right, that's not a dimension anywhere to be found. So I have to go to actually the WT section. Yeah, it's not that. It's not that. That is a gate, it's a how you build it. Let's see. Where is a T section? It's actually, right, see, here to here, that's what I'm looking for, right? Here to here. It's actually Y bar for a WT section. And actually, if you need that for an I-beam, you'll have to find the corresponding WP or the T section and use the Y bar. And so on and so forth. We'll do some examples to have you look it up, but that's just to tell you, because it says X bar doesn't mean you're looking for a quantity called X bar. X bar is the eccentricity, it might be a different symbol. It might be a different symbol than X bar. So look at the picture and reconcile it with the picture of your dimensions. That's where that sentence was going. So case 3, let's go back, let's see, we got case 3. This is all tension members where the tension load is transmitted only by transverse welds. Remember what transverse means? It means perpendicular to the force. So, right, if we have that I-beam again, connect some type of plate to it. And that's my load. Means I only have welds on that side. Perpendicular to the load. And it says your AN is your area of directly connected elements. So if this is W and it has a thickness, right, T, then your AN is equal to your W times your T, because that's the only thing that's actually connected. Case 4, right? This time we're talking about case 3, case 4. Now we only have longitudinal welds. So again, I'm going to draw, see if my I-beam keeps being nice, right? Now I have the same I-beam. And I connect a plate to it. But now my welds are only longitudinal, so they're only parallel to my load. Longitudinal welds parallel to the load. And then it says, it also gives an example of if you have two different length welds. So if L1 doesn't equal L2, right down here it says that then your length that you're using in this equation, right, the W is your width of your plate, right? Your length is equal to the average of your two lengths, but greater than or equal to 4 times the weld size. Right. Case 5, if we have a single gusset concentric within a round HSS, it says if the length of your connection is greater than or equal to 1.3 times your diameter of your HSS, you get to use a shear lag factor of 1. Otherwise, if your length is between, right, 1 and 1.3 of your diameter, you have to use the 1 minus x bar over L, which is just like case 2, right? And it tells you how to calculate that eccentricity, that x bar. X bar is d over pi. So what do you notice? If you have a longer, right, this goes along with what we've talked about before, longer connection equals higher shear lag factor. Right? U starts to go to 1, which means you get to assume more of your cross section is effective. A higher shear lag factor means more of your cross section is being put to work. It's effective in resisting the tensile load. Hopefully I'll say that enough times. And that's what I'm just pointing out that example down there, right? If you have a longer one, you get to equal 1. If you have a shorter one, you have to reduce your shear lag factor, so you're reducing your effective net area because less of your cross-sectional area is actually engaged and subjected to forces. Right? So let's see, case 6. We're just going right down the list, right? Now we have a case 6 is, let's see, this is the first one where we have a single concentric gusset plate. That's what this would look like. side gusset plates. And it gives you the equations for how to calculate your shear lag factors for both of those examples. We're almost done. Okay. Case 7. Let's move that out of the way. This is permitted instead of using case 2. Case 2, you can use case 2 or case 7. And actually it says you can use the less conservative value of the two. So this is basically just a way that if you have 3 or more fasteners in a flange or 4 more in a line in the web, you can just assume a shear lag factor of 0.9, 0.85, or 0.7. You don't have to calculate it. Right? And what those would look like, what it's talking about is it says for a W, M, S, basically any I-beam or the T's cut from their shape, so a WT, a W or a WT. If the flange has 3 or more fasteners in a row, so we're attaching our plate to a flange. For some reason I can't ever do that one. Let's make it longer. Alright, got my plate there. If it has 3 or more fasteners in a row, so in per line the direction of loading, right? So 1, 2, 3. Probably symmetric, so it'd have 1, 2, 3. So this is an I or a T with 3 plus fasteners parallel to that load in flange. Alright, if my load is like that. Alternatively, right, that's the first one. The second one is the same thing but with the web and with 4. Now, if it's the web, and it's 4. 1, 2, 3, 4. again, I or T with 4 plus fasteners parallel to the load, this time in the web. This just means you don't have to use that equation 1 minus x bar over L if you don't want to. You can just use these numbers. You can go back and use case 2, and if you get a higher number for case 2, like if you get 0.92 instead of the 0.9 for your flange connected with 3 or more fasteners, you can use 0.92 if you'd like. Because K7 is just an approximation. So if you have a different number, you can use it. And finally, we're going to look at case 8, which is a special one of case 2, but now instead of focusing on I-beams or the T's of I-beams, we're looking at angles and double angles. Right? An angle would be if only one leg was attached. If both legs are attached, then you can use a shear leg factor of 1. But, right, if we're looking at, let's look at a single angle. It says 4 more fasteners in the line of loading. If we have, say we have a plate on the top leg here. One, two, three, 4. There's 4, and there's also a 3. So single angle or double angle with 3 or 4 in line of loading. Alright, parallel to PU. And an example of like 3 with a double angle would look like, let's see, this is the hardest one to draw. Alright, there's my 2 angles back to back. And let's say I have a plate on either side of and let's say it has 3, right? 1, 2, 3. Now it could be a single angle with 3, it could be a double angle with 4. These are just examples. Right, if you have 3 fasteners, you have a smaller shear lag factor. 4 fasteners, you get up to 0.8. It says with fewer than 3 fasteners, so if you only have 2, you have to go up to case 2. But this is if you have 3 or more. Okay, so those are all of the provisions for shear yielding or not shear, tensile yielding and tensile rupture, incorporating a shear lag factor for your rupture. Looking at the spec. Now I'm going to do a couple of examples for calculating effective areas and then calculating actual capacities. All right.